Let's talk about vector quantities. Again, a vector is anything that has magnitude and direction. So when we talk about magnitude, it's how much, the size, the length, the amount, and that would be like the number. So 30 meters per second, the 30 is the magnitude, but velocity also has direction. Velocity is a vector quantity. We've decided in one-dimensional motion, positive, negative, up, down, left, right, our directions, but now with projectiles, we have angles, right? So these are ways to define directions. So these are some quantities that are vector quantities, right? Displacement is a vector quantity. You have a distance, which is the magnitude, and a direction, which makes it a displacement. And velocity is a vector quantity. You have speed, which is the magnitude part, and direction is what makes it a velocity, right? In this case, it's an angled velocity. And you have acceleration as another vector quantity, right? Downward of gravity, so there's a direction that gravity pulls, and things accelerate in that direction. How much is the 9.8? So it's like if we have something with magnitude or size and direction, we have a vector quantity. Now vectors can be represented with arrows. So when we draw our pictures, if it's a vector quantity, we would put an arrow, and where we point it is the direction, and how long we draw it would reference its magnitude. All right, so let's look at some examples how I would draw a vector. Okay, so a vector A, this little symbol on top of the A is just to say that A is a variable, but it's a vector quantity. So 3 meters to the west, I would draw as an arrow left, right? West on my page, I would draw left. And the length I drew it arbitrarily, let's call that a length of 3 meters, which means vector B, if it's 5 meters, this blue arrow is longer than the 3 meter arrow, right? And it's also pointed a different direction. And there's different ways we can describe direction with angles. So here's a 40-degree angle counterclockwise from the x-axis. So if I'm measuring an angle, I got to measure from somewhere. So the positive x-axis is over here to the right. If I'm pointing that way and I rotate counterclockwise in this direction, right? If I go 40 degrees from there, I will be along a path that this arrow points, right? Coincidentally, I could also describe it with this angle of 50 degrees. And that would be clockwise from the y-axis. So here's the y. I would rotate like a clock towards here 50 degrees and get there. Notice 50 and 40 are complementary. Now, here's another way. Vector C, 2 meters. Again, I drew it a little shorter. It's only 2. Southeast. I didn't give an angle, but southeast is exactly between south and east, so it must be 45 degrees. So I can mark that angle here. And here's another example, 4 meters. I drew it a little bit twice as long as that one. 30 degrees west of south. When you see of, you can think of from. And so west from the south, I would face south. And I go from there towards the west 30 degrees. If I went 90 degrees, I would be going all the way west, but only 30 gets me here. Right? Coincidentally, if I face west and I go south from the west or of the west 60 degrees, I would be in the same direction. So saying 30 degrees west of south or 60 degrees south of west are the same direction. So how do we add vectors together? Well, if I added A, B, C, and D, I would get what we call a resultant, or the answer to a vector problem. All right, and it would be one vector displacement that would get me from start to finish, no different than taking these 4 displacements. Now, in math class, we learn about scalar addition when I just add numbers. If I add the 4 scalar numbers, I'm adding the distances. I would travel a total distance of 14 meters. But that is not what the displacement would be. All right, well, let's look at how we can do this graphically to see my point. Here are those same 4 vectors, drawn with length to be the distance, but the direction component. If I walked a path of A plus B plus C plus D, I would start right here. I put a little I there. I would walk west, then a little bit northwest at that angle, then a little southeast, and then southwest. I would finish right here, which means my overall displacement, the total displacement, would go from the start to the finish in one direct path. And the length of that path would be my resultant, and the angle that I would go would be the direction of that resultant. So I would describe my total displacement as r, which in this case ends up becoming 1.9 meters at 60 degrees clockwise, like a clock, from the positive x, or I can say 60 degrees south of east. Right? That would be kind of an estimate. I don't know if it's actually 1.9, but it looks like if this is 2, then that might be a little less than 2. Maybe it's a little bit more, but it's around 2 from my picture. Right? So the nice thing about addition is I can add in any order and I would still get 14. Vectors work the same way. If I start with the blue vector, then the green, then the gray, then the red, I end up in the same finishing point. I can start with the green, then the blue, then the red, then the gray. At the end of the day, my total displacement r, this black vector, looks about the same no matter how I do it. And so it shows that commutative property of addition that is true with scalars, but it also is true with vectors. So I could actually add vectors in any order, which is kind of a neat property. So let's look at how we would get an exact value, right? So this is a graphical way to do it. And if I did it really carefully with a protractor and a ruler, I could get a value and I can measure that and measure the angle and have an answer. How do we get an exact value? So this is a process we'll use to get an exact one. Here are the 4 vectors again, all right? And what we're going to do is we're going to split them into their x and y pieces, right? So here's A, B, C, and D. And I basically have an x, y table, right? We like setting up tables of variables. And we're going to describe each vector as a piece in the x and a piece in the y. And anything in the x we can add together. That's my x table. Anything in the y we can add together. All right, so let's look at vector A. Well, vector A only points in the west. So west is negative. I put a negative there. It's 3 units long, and it does not point at all in the y direction, so I get to put a 0 there. Vector B points up and to the right. Looks like it's going right and up. Think about your math quadrants. This would be an ordered pair that's a positive, positive one. So it's going to be right in the x, positive, right in the y, or up in the y, positive. Put the signs first. But how much? Well, this is where we can use trig. Just like with a launch velocity that was 40 degrees like this, a displacement, a distance, can be broken down the same way. I can use the same trig. 5 cosine 40 would give me how long the x piece is, and 5 sine 40 would give me the y piece, and I can put those values into this table. Here's this vector. This points down and to the right. So it's to the right, positive in the x, down, it's negative in the y, and at 45 degrees, those two legs are the same, and we calculate to be 1.41. And the last vector is down and to the left, so it's negative in the x and negative in the y. There's my negatives. And how much? We got to do a little bit of trig. We can use the 30-degree angle or the 60, and if I'm careful with my trig, we're going to find that the values in the x, it's left 2 and down 3.46. So we've now broken each vector up, and technically if I'm looking only in the x, I'm going left 3, then right 3.83, then another right move 1.4, and then left again at negative 2. Right? In the y, I'm going 0, then up 3.2, then down 1.4, then down again. And if I do that mathematically, I just add up each column, and I would get a total to the right of 0.24, a total to the left of 1.66. These are what we call the components or the pieces of our answer. They are not the answer, though. They're just the 2 pieces. We've added 4 vectors, and we've now consolidated them into 2. And now I can use these to draw my resultant pieces. I would start here. I would move to the right 2.24, then down 1.66 to get to my finish line, which means my actual answer goes from here, the initial, directly to the final. And hopefully you see the right triangle. There's our angle right in here. And the length of this angled vector, using the Pythagorean theorem, is 1.68. And this angle, I would use the inverse tangent of these 2 legs to get 81 degrees. Right? And so now I can describe my answer, my total displacement, r, as a vector of length 1.68 meters at an angle of 81.8 degrees. And it's measured from this horizontal positive x-axis. So I would say it's clockwise from the x. Or if we call this east, it would be south of or from east. So this is an example of how you break down vectors. In every vector addition problem, we can follow the same process of breaking the vectors into x and y pieces, just like we break a projectile motion problem into x and y directions. Add each x piece, get a total in the x. Add each y, get a total in the y. And then draw our resultant displacement with x and y pieces and do a little trig to finish. And we can add vectors in this way. And again, in my table, I can do any order. I can do b plus a plus c plus d. It wouldn't change my total. Oftentimes, we don't have angled ones for multiple vectors. We might have a bunch that are only in the x or only in the y. We see a lot more zeros in here. But the process remains the same. So this is how we do vector addition. We're going to see this with displacement vectors. We'll do our vector treasure hunt. We're going to see it again when we get into forces and we start adding forces together, because forces have a direction and an amount. Forces are a vector quantity as well. Good luck.